It's like your price.
And I just got the megabytes of all started situation. City bank.
Really, like grab a seat and go here.
Yeah.
Instead of you not. I see. I was like. No, it's not jogging.
Well, the world is run by those who show up.
Might just take a minute on my end.
And,
I'm gonna wait, pick up sure.
took a minute. Sarah, the executive admin.
All right, we're gonna go ahead and run through this agenda while we're waiting for the technical difficulties to get resolved of the email and the megabytes. Welcome back for an update on the results. Dr. Hamel, Dr. Murray, Scott, Polly.
Sure.
Magda's not here, so we may or may not have a treasury report for you at this time. We're not spending a lot of money, and we spent $1,000 for each of the universities, UAA, UAF for their steel bridges. Probably just keep continuing that. Other than that, we paid our NC SEA dues for the webinars to Reed Middleton. So we've got the webinars that everybody loves. I'm Nikolai Petrov, if anybody doesn't know me. Been president a couple times until I can get, maybe Jake to take it back over someday, or if anybody else wants to be a vice president. We're actively looking for leadership in this group. Some cool news, ASCE foundation standards coming up. Our ASCE is coming up with a new foundation standard. Appendix A is permafrost, and they reached out to the Alaska engineering community. So there's a couple people on the thread. If anybody wants to get involved, we'll probably have Sterling send an email to the group. Steve Halcomb with Devise Engineering is chairing it. So I reached out to him, and then he reached out to me saying he'd like to, how do I get more involved? At the same time, Ralph was saying, hey, who can run this? So, thank you, Stephen. He's looking for writers and reviewers, and he wants to keep those separate so that we got a good doing that. Presentation outreach. We're looking for presenters. So far, I've been talking to a guy with, oops, I'm not sharing the rights. There we go, big file. Hold on, pause everybody.
Oh, is that what you call it?
That's what I call it.
So we're. Magda, you got a treasury report?
Yes, I do.
Look at that timing. There's more chairs in the closet if we need to pull out more chairs. There's a couple over here. There's one next to me. All right, back to our agenda. Sorry about that, everybody. So this guy made shuriken bolts. I heard him on a podcast, engineering podcast or something like that a while ago. He works with Atlas Tube. So I reached out to him and asked him if he could come up sometime this summer or even do a virtual presentation. But basically, it's a bolt that goes, it's a bolt backing that goes inside HSS, so you can splice HSS tubes. But just hearing him on this podcast, he sounded like a pretty cool guy to listen to. So reached out to him on LinkedIn. He's talking to the wife about when he can get up here. But we still have May 21st, July 23rd, September 17th, and November 19th. So if anybody has cool projects they would like to present on or any cool ideas, other than that, we're going to be filled with vendors that want to come present on their products, which is good, but cool projects are always a little better. PDHs, everybody, we're on a renewal year, I believe, so don't forget your PDHs. Next, NCSEA webinars, April 3rd. It's on mass timber connection design. Thanks to Reed Middleton, Latoya Watson is who you RSVP through. Sterling had to leave early, so he went and got the lunches for me, which is much appreciated. Don't forget to sign in. Anybody online? I wasn't even sharing that screen. Okay. Anybody online? And right here. We're going to take a screenshot. This meeting is going to be recorded so we can put the presentation on our webpage later. With that, I'll go to share the screen. And do you want to just tell me when I'm supposed to hit go? So function F5, I believe. All right, after that, I'm gonna hand it off to Dr. Scott Hamel and Dr. Paul Murray. Assessing the performance of non-code compliant wood shear walls.
Treasure report.
Oh, Mac, that's where we going. We got the treasury report. Mac is gonna go. I gave him a brief summary already while we were waiting for you.
All right, okay, so it's been 2 months since our last meeting, and actually the 2 months were really great our because we received plenty of corporate memberships, and also a lot of members renew their membership. So we all, really thankful for that. So we actually collected over 7,000 in a membership or within that. I mean, since beginning of this year. We did provide donation for bridge teams for this year. So we did pay $1,000 towards the UAA team and also $1,000 towards the Fairbanks team. So both teams received our support. We were able to, we also renewed our membership with the
SEA.
not yet, CEA. And we also purchased the webinars through them, so we're able to
Richard.
have you guys receiving the emails regarding the webinars. Anyway, so currently in our account, we have $17,503.96. That's it. Thank you.
All right. Hey, Jim,
We do that, did SEAAK contribute to the, one of the scholarship funds that you may or you have to prepare, or did we grant a scholarship to prepare? No.
We didn't get reached out to or contribute to that. Just slipped the radar. We just did the Steel Bridge.
Okay.
So
We'll want to add it to the.
Sure.
Go ahead.
And put on my
Start
other,
as a different person.
put on my chair hat.
Yeah, go ahead, please.
And so one of the some of you already know this, but the advisory board, the civil engineering advisory board, which is a little bit different from the college advisory board, has been working really hard to increase the pool of civil engineers, which I'm sure you all appreciate. And so one of the strategies for that is to generate, we created a foundation account so that all the firms in town can make donations. And the purpose of which is to provide scholarships for high school seniors. And then also, potentially more valuable, the fund is loose enough that we can actually pay for some advertising. So be sort of ramping up some advertising, and it'll be a little bit UAA slanted, but in general, it'll actually be more sort of like, hey, be a civil or structural engineer. There's a lot of that operate. So that's the goal. And then, so I can talk to the SEAAK board about that. I've been sort of making the rounds with all the companies. I haven't hit all of them yet. Or have I hit all the organizations yet? But we've already raised about $20,000. So we're already in pretty good shape. Our goal for the year was 40,000. Yeah, so we're about. But on that note, today is actually also the 49 hours of giving. So UAA has an annual big fundraiser, happens today, 49 hours. And so we're actually looking for donations in our other fund. One of which I did a bridge, and one of which my pitch is to, give us money.
Or after we were at Barrett's house.
is somebody unmuted on the online there? If you are, please mute.
If you want to sit here, we're
No problem, Chair, maybe.
There's one in the closet.
Okay.
All right, on to the presentation. Just
Nikolai, do you want an ALS report? Where does that?
if you have one, we would love one.
They're very short. We're going through the sunset right now, trying to break up the electromechanical seat into an electrical seat and mechanical seat, add into your design sheet. Do a whole bunch of stuff that's kind of housekeeping, and also in interior design. We've been talking with a lot of the other state boards about the SE exam. You don't know, it's now computer-based, so instead of 2 one-day tests, and you have to pass both the breadth and the depth of lateral or breadth and depth of vertical to pass it, you now have 4 tests that are 5 hours long, or you have 5 hours to do it in anyway. And you can pass any one of those and hang on to that. However, the pass rates have been dismally low, like 17% in the first 2 for the buildings and about 38% for the bridges. Part of the problem is that a number of the questions require you to look up 3 different things in 3 different books, and the download time on the PDF is very, very slow. And we've told NCAAS this. Also, they only have 1 monitor, so you can't have one thing on one monitor and another one on another. But that's where Pearson U does it, and there's no way we're going to get that to change. However, they can start rewriting tests, questions to not have you have to look up as many things. But speaking of which, there's currently a PAC study out there. You can go to the NCAAS site, which is the something in knowledge study. Basically, they ask what you think could be on the test, what's important, what's very important, what's not so important for both bridges and buildings. And it takes about 20 minutes to go through there so that they know what kind of questions should be on this exam, what they can kind of not be testing you on. And our next meeting is our next meeting is a special meeting about the sunset bill in April, but then our next regular meeting is in May. And Sterling is now the vice chair and I'm the recording secretary. And Edley and Eddie, the landscape architect, is going to start being the chair as of July 1.
So to piggyback on that, if you guys if it's come to our attention that the NCAAS equal to FE and PE, there's only 8 spots to take a test in Anchorage and 4 in Fairbanks. So come to our attention that sometimes our students can't get a spot. So if you guys have EITs or recent grads who are trying to take the test and are having trouble, let us know, because we're trying to get UAA, which already has a testing center, to also be NCAAS for testing center. So they're giving us some guff about it. So
Yeah.
evidence we can get.
And that's 8 seats per time slot,
Right.
so that's 16 per day, essentially. But I don't know if it's 365 days a week, but it's at least 5 or 6 days a week. So you can take it anywhere through the year. You can fly to Honolulu and take it if you wanted to while you're on vacation. Because you can you don't have to take the test in Alaska to get licensed in Alaska. You can take it anywhere that Pearson U has the testing center.
Is there any realistic alternative to Pearson U? You know, if they have their servers, you know, with references are so slow, you have to have 3, and you can only have 1 monitor. Pearson U says tough shit. Is there any realistic alternative?
Not without a whole lot of hardware, right? Switching the provider, because they do all of the evaluation of the exams and whether the question's too hard or too easy, and do a psychometric analysis of the exams. And I think there are probably others out there, but they've been working with them for probably a dozen years now since the FE went live.
So do you know if there's any reason why you can't use your references but still do online tests?
Because they don't want you to bring notes in on those references. They want you to just use the references. Or hide other stuff in there, you know, they won't have to check all that. You basically can't have anything in the testing center. They make you take everything out of your pocket and put it into a little locker that you have a key for. So you're in there with nothing but pencil that they give you and the paper and the machine.
Did those people actually took the test?
Yeah, they
They did?
have licensed engineers who take the test after each session so that they can also assess whether those questions were good, bad, or different. So they can develop a cut score.
I mean, I'm talking about the people who decided that, because I mean, when you're practicing EPA, it's like you're not necessarily know everything in a one material, one discipline. So knowing everything and being able to do that on a 5-hour test and be proficient without your notes, that's not realistic.
70% of people are passing.
Yeah, exactly.
Well, when they first went to and the first time that they offered the SE in paper and pencil, it was about a 17% pass rate. It's just a new system and people aren't used to it yet, and it will go up. Pass rates in all the tests were down the first time they offered it on computer. And the structural exam has always been the lowest pass rate of any of the exams.
Okay, with that, we are gonna get started, and just to let everybody know, I'm gonna let this meeting run over. We have it until 1:30. If anybody has to leave early, just do it quietly.
Okay, well, we have about 30 slides, so we'll do it 30 minutes. So most of you, a lot of you have seen probably our earlier presentations, middle of it. And so this was our project funded by FEMA.
So in November of 20, remember there was a 93.1 earthquake, which caused pretty extensive shaking throughout the Anchorage and Eagle River. This is a map of requests for assistance. So basically, this is one measure of damage. This is how many people ask FEMA, I believe, for help repairing or demolishing their house. And so we can see that we have a much higher concentration of requests for assistance. So this is kind of indicative of also what we saw. The section is that there was more damage in Eagle River. And unfortunately, the one ground motion sensor in Eagle River was offline during the earthquake. So we only have an estimate of shaking there based on the due diligence surveys, which kind of correlate people's experiences that they've observed to ground motion intensity. And based on those surveys, shaking was approximately the same within the Anchorage and Eagle River. And so the question then is, why was there more damage in Eagle River? And is it because building codes are not enforced outside of this green? So this is just that map of the ground motion intensity. So the triangles are actual ground motion sensors, and the circles are the kind of aggregated survey data. And then this is just the spectra recorded and time spectra for our building, the PIB. And so you can see that shaking was far below both the design and the MCU level. And this is of course an old ASC 7 spectra. And so there were some sites where shaking exceeded design, but for the most part, this was not a huge shaking intensity event, even though the magnitude of the earthquake was relatively large.
And I would point out the 0.2 shaking here. Which
Yes,
will
yeah.
become relevant here.
So,
Short periods.
yeah.
Okay, so this was the methodology that we came up with after FEMA and some of the folks sort of asked us to do this project. Since I wrote the proposal, I should say that it was definitely a bit off more than I chew here. This was not something that I had a lot of background in. So definitely the entire project was underfunded. Better way to say that. And there was way more work to do and learning to happen than we had funding for. And it turned out fortuitously that I could not get a graduate. Originally, it was supposed to be a master's student for years. I couldn't get one because nobody wanted to work for me. That's,
That's not true.
it's nobody in Alaska at the time wanted to work for me. And so I ended up converting it to a postdoc. That's how Dr. Murry came to us. And that was really, it turned out to be a really good thing because I didn't really know that much about seismic modeling to get it. So it was a rough project with a master's student. So, and that'll come around again near the end of the presentation. So this was the idea behind the project. And all the other thing is that the agreement was signed in like March of 2020. So it started off well, you know, as soon as everything went into lockdown as soon as we got money. So we started out with interviews. We talked to a bunch of you and other people about what they saw, what you all saw in Eagle River, and in Anchorage. And then sort of using that data and using that, we built a bunch of walls in the lab. We tested a bunch of walls in the lab. That's kind of the last time we did this presentation. We had some results from that. And then the part that's happened since then is mostly the modeling part. So we'll try to skip through some of go kind of fast on the experimental part. So. Oh.
Yeah, so just in both reading the reports from ERI, which is the Earthquake and Shear Research Institute, and chatting with folks that did these inspections, kind of the recurring themes were that either the number or the size of the nails was below design, or sometimes both. A big one was with the T111 siding. There's this overlap. A lot of people just put one nail in that overlap, and so each panel is nailed through a really thin portion of the plywood. So the theory was that maybe that wasn't as strong, but that was a really common way of building. They saw lots of houses with no hold downs or anchor bolts or any bolts not tightened. And a lot of the design, kind of not just the construction, but the design of the houses featured like full walled windows, without maybe accounting for that in the structural design. One of the things the fasteners were overdriven. The walls lacked blocking where they had horizontal plywood. And occasionally we'd see mud sills with no nails, which looked like maybe they just forgot. Yeah, and then poor material quality. You can buy like really thin T111 only in Vasilla. We didn't actually test that one, but there's sort of variety.
We did test six penny nails. We also heard that there were some 6 penny nails being driven. That was
Finishing nails.
Finishing nails.
Those were not.
That's what they called it. Finishing nails. So, but the top two are bolded because that based on all the interviews we did, that seemed to be the most common. There's a lot of talk of like, obviously when you go out there and you see something alarming, it triggers your memory, right? Like somebody saw, they're putting the hold downs in, everything was perfect, except they forgot to put the nut on the hold down, right? Spend all the money there, but doing nothing. And those we wouldn't call those things common. Saw them, but the top two seem to be so this was our setup, which many of you have seen on our little spawn floor. We basically built the walls. There's a whole ASTM and a bunch of, I guess they're not ERI, but earthquakes, I guess they're all ASTM standards, or ICC. And so for the most part, we tried as best we could to, mimic the walls. And so there's a lot of this is the standards. The beam on top has to have certain stuff. The bracing has to have certain characteristics. The hold downs are actually connected to the steel, which is connected to the strong floor, etc. And then the things of interest probably the things that varied, of course, were the sheathing type and the nailing. And then we only did one test without hold downs because it was a pretty silly test. The wall just started actually walking up its nails because there's not really any weight or mass on top of this thing. And so every time you pushed it, it would it's basically just had the nails coming up from the connecting the
sill plate nails.
Sill plate to the studs.
Yeah.
So that the whole thing just sort of walked up. So that was silly. So we just really did one of those. We also did a naked wall, which was kind of fun, which is basically a wall with no sheeting, just to see what the baseline of a bunch of studs moving back and forth was. But that was interesting. And so then the protocol for the test is called the Curie protocol. And you can kind of see it there. It's so that if you can't read that, this is displacement over time. It's about 5 minutes long, about 300 seconds. So it's kind of slow. It's not an actual dynamic shake table test. So it takes a few minutes. It's kind of slow, but it starts out small and then it kind of pushes further and further and further. And we'll see that when we get to this stuff. It was a lot of wall building. That was less fun.
I personally overdrove some nails.
Yeah, so we did learn a lot though. And the other thing that we learned is the
Did you use a hammer or a nail gun?
Well,
both.
it's a hammer for the old mounds,
Yeah,
which was like 52 and penny nails per side and like precise. But the shooting was all nail gun.
one of the things we learned was that the prescriptive requirements for, like how many nails, if you have a double stud in the middle, how many nails do you attach the double stud with and what size, all those, how many nails do you attach the vertical studs to the top plate, bottom plate? A lot of that stuff is either hard to find, or when you do find it, it's a little bit contradictory sometimes, depending on whether you're looking at IRC or the NDS. And so that there was a huge learning curve there of like, wow, the carpenters are not like, they're struggling with what they've been given to build a wall correctly, right? Building a wall correctly is not that easy. So that was kind of interesting for us. So this is some of the failure mechanisms that we saw. In general, for the plywood, which was the T111, the nails tended to back out. In the OSB, the nails tended to rip through, which you can kind of imagine, because the OSB has way less ability to grab the nail. Particularly if you did a couple of tests where we drove both nails into the same stud, right? So you only had like 3/8 of an inch of OSB. So that didn't go that well. And then this was staples. Staples tended to pull through the OSB. So those were generally, we had all kinds of other random failures where, the top plate would rip off. Sometimes we had like really tight space. It was also a good experience for, if you go and look at the SPIDWIZ, it tells you that you can actually use 2-inch nails that are 2 inches on center. And a lot of framers will not do that because it's ridiculous. And we saw that, right? We did 3 inches on center and it was already kind of ridiculous. To get 2 inches on center and it's just shredding the 2x4. Okay.
Yeah.
So this is basically we're imparting a displacement and measuring the force, and so then we can plot it, our hysteretic curve. And there are certain limit states that are defined in this ASTM standard. So the yield limit state is basically where we start to lose stiffness. So our nails start to pull out, the OSB is crushing around the nails, and whatever it is that makes the wall less stiff. And then we have our kind of peak up here in red. And then we have what we call the ultimate limit state, or not what we call the ultimate limit state. And this is another one that is a little bit contradictory, where sometimes it's almost always correlated with a 20% loss in strength. So whenever you are resisting 20% less than your peak force, but some of them will say it's the last peak. So here before you cross 20%, some will say it's the first after. Some will say you can interpolate along this line. So there's a lot of these things that are a little bit fuzzy, I guess, for lack of a better word. And so the couple kind of key parameters that we looked for were the stiffness of the wall, so kind of the initial absolute yield, and ductility, which is the ratio of the displacement at this ultimate state, the 20% loss, versus when you start to yield, and then our strength, which is probably the most self-explanatory, which is the highest force that the wall ever resisted during the
Yeah, the notation of like professional seismic design, professional not seismic design, researcher seismic design, researcher not seismic design, like it's like a bunch of totally different people. They use different terminologies. And to sort of, it was an interesting approach. So I had to hit it.
Oh, sorry about that. There we go.
All right, so here's some results. I apologize, there's a lot of numbers here, but we tried to make it somewhat clear. So we did do box nails versus common nails, and I converted this to the average shear. So this is like, it's the average peak shear is the appropriate technical term. And previously we gave this in pounds, so I converted it to pounds per linear foot. We had an 8-foot wall because that's what NDS gives, right? That might be in your head. And you can see that there's not a huge difference between the box nails and the common nails. They both, for 3 inches on center, they both come up with about 1,100 pounds per linear foot. Interestingly enough, these numbers actually correlate pretty well with some of the design values for in SPIDWIZ, which is interesting because these are peak values, and those are design values. Of course, then there's a the 0.5 peak factor on there, and so that brings it down to half. And so it was interesting to just see that those two numbers really have nothing to do with each other, or they do, but it's a weird relationship because this is a side, this is a hysteretic test, and so. But they actually came in, for the most part, pretty similar to each other. And so you can kind of see as we go down, the spacing increases from 3 inches to 6 inches to 12 inches. It basically cuts in half each time, which kind of makes sense, right? You have half the nails, you get half the strength. Probably more interesting was the ductility numbers, right? So you see, and you'll see this a little bit on the next slide. You get really high ductilities with really low nails, but
Can you
that's
explain those units on ductility, inches per inch? What does that mean?
so it's the
ratio between the displacement at your ultimate state versus your yield.
Oh, okay.
So it's
yeah.
kind of unitless, but
Okay.
it's an inch over. Yeah.
Yeah,
And then the other thing before we go to the next one, you'll see that the staples, in general, the staples correlated, the strength correlated pretty well with what you find in like SPIDWIZ. So if you have, the equivalent 6 inches on center nails is, I think it's 3 inches on center for 16 gauge staples, maybe. Then those kind of correlated pretty well in terms of strength, but not so much in terms of ductility. And so, and then the other thing that we saw was the T111. We didn't see a huge drop in strength or ductility by using the single row of nails. It's kind of interesting. We expected more loss of strength, but it kind of makes some sense. You still have all the nails around the outside, so you're just looking to see.
Did you guys note any results for that? Because you only had one seam on your T111, so it was kind of like.
We did one of those, and we were like, this doesn't make any sense. So we actually did two. So we changed the wall so that we had a like 2.4.2. Yeah, so we had 2 seams. Yeah. More would have been better, I think, but
Need a bigger strong cord.
yeah, we need a bigger strong board. Those donation. Okay, next slide. Bill has more fun. All right, so here's kind of where you see the difference in ductility. So here you can kind of see that ductility goes up here, but it's really because the strength is so low, right? It's because you're taking this 80%, or it's really flat here because it's so weak. So you're taking that 80% strength, which is like way out here, and dividing it by your initial yield strength, which is way in there. And so you end up with these huge ductility numbers, which if you just are focusing on ductility, you're like, this is great, right? But then the strength is so low that that's not really that helpful. This is kind of what you really want to see is as much ductility as you can get. You want this strength to last as long as it can before it drops. So here's a version, here's the opposite, right? Low ductility, high strength. That's what you get with like a really tight fasteners. I think we have a bunch of comparisons too.
Sorry about
Yeah,
that.
this one. Yeah, so here you can see the difference between nails and staples. And this one was probably one of the most surprising things, right? We saw that, even though the SPIDWIZ gives you basically, or the IRC actually gives you the same equivalent, right? Nails at 6 versus staples at 3. And the strengths are sort of comparable, but you get way more ductility out of the nails, which kind of makes sense when you see the failures, because the staples, they're so little that they just end up ripping through the OSB edges, whereas the nails will bend back and forth before they let go. So you just get a whole lot more ductility out of that. And we had some contractors, framers, who told us that they prefer to use 14 gauge staples, which I remember they are not even in the code anymore.
They used to be, but
They used to be. They got rid of them, and then they were like, I think 18 gauge. They also had 18 gauge. It's like 3 years ago. 18 gauge is not in the code, but people were using them, and so we tested 14, 16, and 18. I think, and it's actually really hard to find a 14 gauge staple gun. Struggled with that. So
we ended up farming, like someone at the beauty had one and went into us.
Got to give it back.
No, we gave it back, we just didn't remember those. I brought it back.
But in general, all of the tests, the 14 gauge didn't actually improve much because, even though it grabs way better, it doesn't actually have that much more capacity in shear, which is what we're after. And so, the 16, but in general, the staples were just way less ductile than the nails. Next one is, oh yeah, this is the box versus common. They were essentially the same. So they accidentally put in box. Give them a shrug and say, don't do that again.
But it's also really hard to find common.
But yeah,
You have to go to SBS and not, like Home Depot sells black nail.
yeah. And of course, they don't say box nails, right? Because they're all nail guns. So they say the diameter and the length. So it's using if you don't have a gag. It's a mess. Okay. Okay, so here's our structure. So moving into the modeling portion, we designed 3 structures, two-story houses and a 1-story house. And of course, we used Anchorage. And this is right. We used it, didn't put R 6.5. And so that's where we ended up with the 0.17. So this is our, so we sort of based the houses on perforated walls with 8-penny nails at 6 inches or 3 inches. So we had the 1-story house. I think maybe the next slide shows all 3 houses. Yeah, it's okay. Never mind. We had a 1-story house that was designed. Basically, we gave it enough wall to get to the spin width limits on 6-inch on center spacing. Same with a 2-story house. And then we did a 2-story house where we basically added more windows until we needed 3-inch spacing. So we basically have 3 houses and they're all designed pretty close to the leading edge of the amount of shear wall and windows that you need.
So I took Scott's designs, maybe the next slide. And I built the OpenSeas model. So OpenSeas is the open system for earthquake engineering simulation, if you have not had the pleasure. And it is open source software. You're a little tricky. Let's say another conversation. But basically, I took our test walls and I calibrated a section kind of just this portal frame with the diagonal strut. And then we capture the nonlinear behavior of the wall in this calibrated strut, which is the pinching form material. And so we calibrate kind of this 8x8 wall to the test data, and then we put that into a nonlinear model. So it's a 3D model that can take, you can simulate ground motions. And I don't know if I have, I don't think I have that without. There is a lot of question marks about modeling with structures. So one of the big ones is whether a rigid diaphragm is an appropriate model. It's all about the relative stiffness between your walls and your diaphragm. And then the other is what your appropriate level of damping should be. And so we kind of used what other people have done with their wood models, and we'll talk a little bit more about this FEMA report. But the phrase, all models are wrong, but some models are useful, is a real guiding light for me. And will become, and so anyway, so we build these models that can capture the nonlinear behavior, they can simulate collapse, and we can measure things like the drift, or we can assess the period of the structure before we start a ground motion and then after. We apply gravity loads and masses throughout the model. And then we run, we can go to the next one, what's called incremental dynamic analysis, or IDA. And so the goal here is to figure out what the model and what the building would do in a whole bunch of different ground motions at increasing intensities. And so this is kind of the output of the IDA is a drift response, or just the peak drifts, depending on how many recording files you want to generate. And basically you can see that as the line gets darker, the ground motion intensity is getting larger. And so our drifts are getting larger as we go. And so what we're looking for in this case is, what is the ground motion intensity that causes collapse. And what is collapse? We went with 10% drift, it's kind of a standard value. And the ground motions that we use, there's 22 pairs that are part of this kind of standard set that FEMA project came up with that represent diversity in spectral shape and duration and kind of distance from the well, but they're all for far field simulations. So where the epicenter is a bit farther from the site, which is appropriate for Anchorage.
Before you get into that, so I think it's worth mentioning, if you haven't already picked up on it, that this is like complicated and pretty niche, and like there's not a ton of people that do this. It seems like every time all the papers written by the same 10 people, they're all in California and Washington, Colorado. But this, I think it's worth, remembering that this is not like simple. It's not like plugging in the RISA model, right? Like this is like, the software, is it the guy, paper?
Michael Scott.
Scott, yeah.
But different.
Yeah.
But he has a great blog.
He's got a blog, and like there's all this, it's all Python based, and it's really not, it's not commercial, right? We're not doing something here that's like, hey, here's how you do it, and there's someone that teaches this or leading edge research, right? So
The best way to get help for the problem is there's a Facebook group where you can help Michael Scott is online. He has a blog that sometimes you can find the answer to your question in this immense history of blog posts. Or like there was a model that was developed. So Curie was the Consortium for University Research of Earthquake Engineering. And they came up with that cyclic drift input. And they also created a model for wood frame shear walls called SEAAK. I was like, great, I will use this. And then I was at a conference at a talk on CLT walls, but kind of similar. And she said that they started with SEAAK and then they switched to pinching 4. And I said, why did you do that? Or how did you get SEAAK to work? I've been fighting with it for like 4 months. And she was like, oh yeah, it stopped working, but nobody updates the documentation. No one. So there have been a lot of
doesn't work. No, don't do that.
like that. So it's definitely not. I would not wish it upon my closest enemies. But it does when it works. It's pretty neat. And so we ran this set of 22 ground motions, and we increased the ground motion intensity here in the y-axis, and then measure the peak drift kind of in any direction on any story in the model during that ground motion. And so if you follow just kind of one color, this one, we kind of have an initial linear start. So as our ground motion intensity ramps up, our forces ramps up, our drifts ramp up, and then as we start to level out, then we approach this collapse threshold. And this is a bit of an older figure, so we have kind of this funky, called this resurrection, where I have a case where the ground motion shoves the building back in the other direction, which is part of why you run 22 different ground motions instead of just ramping up, the 2018 earthquake and saying like, this is collapse. So then we can look at.
Would you please comment on your axes? I can't quite read them. Would you?
Oh, yeah.
What's X, what's Y in each one?
So the Y is the spectral acceleration for a short period. So T is 0.2 seconds. And the X is peak story drift. So that's kind of in any direction.
Okay.
So like each one of these triangles is essentially running an analysis of our building through one ground motion at one density. So we started with 0.2 G sort of level, meaning that the worst case shaking in that particular earthquake is at 0.2 G, and then run the motion, see what the building does, find the biggest drift, and that's your point. And you do it again at 0.4 G and 0.6 G and 1 G, and do it again for the other 21 ground motions, and then you have. So.
And then the second graph?
So then we take the level that caused collapse. So for this orange one, for example, that would be 1.6 G. And we collect those into this distribution, which then we can fit our cumulative distribution function. And so this is, if we go up, so this is the same as the y-axis on the other plot. Thanks, Anna. And so at 1.2 G, none of the ground motions have collapsed.
Interesting.
At 1.4 and 6 G, we've had one of the ground motions has collapsed. And so the black lines here are kind of the the count probability, and then you're fitting a log normal cumulative distribution function to this. And this allows us to compare or kind of equate a ground motion intensity to a probability that that ground motion will cause collapse of the structure at that intensity. So if you have a 2G earthquake here, the spectral acceleration of 2G, and you go up, then you could expect about a 25% probability of collapse in that ground motion. Similarly, you could say your median collapse capacity is 0.5, comes out to here, and that's 2.4 G. So these are a really helpful tool. They're called the collapse fragility curve, and they're really helpful for kind of comparing what do I expect to see, kind of design, like comparing a 3-inch nail to a 6-inch nail, or if this is my design earthquake or my site, what is my probability of collapse in a design or in an MCER couple earthquake?
I think it's important to sort of remember too, that this is, each one of these CDF curves is one building at different earthquakes, right? Not a population of buildings during one. So we only did one building in this example, and we applied 22 earthquakes. So it is a probability of collapse, but it's not what we think of in terms of like how many buildings actually fell down in X earthquake. Right?
But ideally, this matches,
Ideally.
if you have like half of your building stock collapses, then you want to be at a 50% probability of collapse. I mean, ideally, none of your buildings collapse, obviously.
Oh, hey, 3.
Yeah, there's our 3 buildings. So these are our 3 buildings. You can see the mass in kips, which of course is silly, but mass is not kips. But so those are kind of what the 3 buildings look like. Yeah, move that up. Next slide. They're a little bit hard to read, and we'll zoom in a minute. But what you're looking at basically is each color is a different set of tested fastener and spacing. So the orange one is 8 penny nails at 3, and the green one is 8 penny nails at 6. And so, and then we did, each structure basically. And so what you can see is what you would expect to see, which is that and then the other figure that we didn't put in here is that, in which we kind of went through really quick, is that you do take the wall and apply pushover analysis to make sure that it matches what you have in the lab, right? So we have basically a pushover, meaning like, force versus displacement of the top of the wall, and you've got that curve from the lab, and so we do that in the model prior to all this, and make them match, right? So in theory, you're building, force versus displacement curve is the same as your experimental wall. So, and so what you see is what you would expect, which is that you get a, so if you think of this as Anchorage, right? This is the MCER for Anchorage. It's about, depending on which code you're talking about, 1.5, 0.8 G at 0.27. And so if you then look at the probabilities where that ground motion intersects these curves, then we get the probability of collapse of each one of these fastener spacings, right? So for the 1-story house, your probability of collapse at an MCER for 3-inch nails is somewhere in the neighborhood of 10%. At 6 inches on center, it's somewhere in the neighborhood of 30%. And interestingly enough, the 2-story house is way better, right? So we have 3-inch on center nails, you get 0% basically. And then you're at 10% for 6-inch nails. And I think the T111 is also at 10%. So, and it gets, as it shifts sort of to the left, things are getting worse, right? But some of these really bad ones, like the T111 single row, and the 8 penny nails at 12 inches on center are way up here. The probability of collapse of 60%, basically at a maximum severe. So these are our sort of initial results.
So your 2-story house is better than your 1-story house for an earthquake?
Yes, but the reason for that we agonized about that a bunch. But I think that the reason for that is because the one-story house has almost no wall. The one-story house ends up with, I think, 8 feet of wall because there's so little mass that you only end up with an 8-foot wall. It's holding up the entire building, 8-foot shear wall on each side. Whereas the 2-story house it's the whole wall actually, but it's perforated depending on the direction. So you end up with, because you have, the top story has less shear wall, and then the bottom story has to have more because it's got 2 levels. So we ran it a couple of times and spent a lot of time on it. That's kind of what became so little wall. Okay, next is something. Oh, here's a zoom in of so this is sort of the 2-story, 6-inch on the center is sort of our primary house, which is in the middle, previous slide. So you can kind of zoom in. And we didn't mention yet, but if you read the commentary of chapter 2 of ASC, or chapter 1 of ASC 7, it talks about how the target reliability or probability of collapse for any building is about 10%, right? Which is maybe high if you think about how many buildings you want to fall down. But that is for the maximum considered earthquake, not the design. That's kind of what we were shooting for. And what you see in our initial results, you see, wow, this works really well, right? Like we did all this work and it turned out that the design house, which is 6 inches on center, which is the green line, the MCER earthquake hits almost exactly that 10%. Rejoicing, right? Like our model worked. Incredible. Like,
Foreshadowing.
some foreshadowing here. All right, next slide. So these were some conclusions early on of us, kind of coming to conclusions, right? Which is that fasteners, the fasteners become especially important in houses with few walls, right? So this is a bit of the discussion of the 1-story wall, right? And you have very little wall that's important. And as I kind of already alluded to earlier, it's both the ductility and the strength together that matter, not just the strength or just the ductility. You can kind of see that in these results because the 3-inch, or for example, the staples, even though they're, well, actually, in this one they do better.
But if you compare like their probability of collapse at a lower intensity ground motion
Oh, yeah.
versus the median, so the sharper curve means it's a faster drop off. As the ground motion increments up a little bit more, they more suddenly are more likely to collapse. And that's kind of reflected from that sudden drop in strength that we see when we tested the staples.
Yeah, so the staple line is essentially steeper than the nail line because you hit the point where they're going to go and they just go. At any like
Ductility.
no warning. Yeah.
They're pretty bad though. It's a fun test.
Yeah, they all snap and yeah. You go back one. I think it was. So I threw this up in terms of numbers, just in case it's hard to read those plots. What you see in these numbers is the same thing, just basically that, the middle, the SF2, which is our 6 inches on center nail, we're under our 10%, and the SF3, which is 3 inches on center, we're under 10%, and then you can see they go up rapidly from there. Basically meaning, if you don't space your nails at the appropriate spacing, or you don't have enough shear wall, then your probability of collapse increases dramatically, right, and rapidly.
What's your SF 1, 2, 3 again? Just refresh.
So
The
there's
story
one
has-
story, the 2-story, and then that story. Yeah.
The single family.
Yeah, and again, again, the 1-story, we were struggling to kind of get it to work right. And again, I think it's because we had such a small amount of wall. So maybe we'll foreshadow. Okay, next slide. Okay, so it turns out, and I'm sure that all of you have had this experience, that as I said, this project was chronically underfunded, and both Polly and I were teaching a lot at the same time as we were doing this project. And technically, PhD or not, Polly's an EIT. And so falls to me to be actually review her work, which I did not. And there was a mistake in the model, which was a pretty one line of code. In hundreds and hundreds of lines. It's not really, and I'm not even sure it was a mistake. I think more so it was a like, oh, we'll put this in for now until it's working, and then we'll come back later and fix it between the two. And so we were doing more work on a new project, which involves SIFs. It's basically the same project except for SIFs. And we discovered that the masses that she had put in for the buildings originally were way low. Did anyone catch that? I had them up there and no one said, oh, those masses look kind of low, right? But they were kind of low. We will spare you the flipping back 20 slides, right? But it was, I think it's
like 11.
11 and 14 were the masses, right? So if you think about a house that size and you do the math real quick, there's no way that you can get, a house built of 11, 30, basically a 40 by 30 house with 11 kips of mass as entire roof, including snow. % snow. So these are the appropriate masses. And so we reran the models with the appropriate masses, and it comes out much worse. It turns out that mass is a really big deal in this. It's super sensitive to mass, as you might imagine. One of the things that is interesting to that though is or I think in Polly's defense, she did check the periods and they seemed reasonable, right? So because that's one of the things we check in these models, right? Is you have X mass, you have X stiffness, you should come up with roughly the period of about 22.3 seconds, and that's what we got. It turns out that when we reran it, we got a period of more than 0.4 to 0.5 seconds. So these houses are actually like swaying a lot more than you would expect a house to. Go back to that in a minute. But this is kind of what it goes.
And I should say that this type of analysis is most sensitive to the period and the damping ratio. And so I wouldn't say that our initial results were totally out of whack, but it's an interesting balance. We'll talk about more of like, what do you include in your model? What's conservative? Because if you're doing a regular design, typically you want to be conservative. And so maybe you don't count the contribution of like sheetrock, or screwed into your frame. But if you're trying to accurately model something, then you do include all of the masses. That is, yeah. And to Scott's credit, he did ask, like, what do you have in the mass? And I was like, yeah, it's right here. It's, PSF, and I was basically not including the walls.
Yeah, you have about 80% of the roof and floor, but no walls. So it's amazing that the walls actually had that much of an effect. And we did include in the second round, we did include interior walls as well, because that was what my design, and this is where the disconnect was. Like, I did the design included all the stuff, and then she did the modeling, and it didn't include all this stuff, essentially walls. So you see the new version. What you see is, some of the structures under some of the ground motions are failing at 0.6 G, and median has gone down from way up here down to below the MCER, which is about 1.2 G. And interestingly, these two houses, these are the two designs. I picked these two because these are the design cases, right? SF2 is designed, it's a 2-story house with 6-inch center nailing. That one's a 2-story house with 3-inch center nailing. And so you'll notice that the medians are about the same, right? So it's sort of working in the sense that the design is giving us, this model. So, and then this is what the CDFs look like, which is not nearly as nice or as fun as the previous ones. And
maybe even concerning.
Maybe concerning, right? The probability of collapse of a house designed with 6-inch nailing, but you happen to put in 3-inch nailing is about 45%, right? Which doesn't seem right. And so we wondered, well, what the heck is going on with this model? And next slide, no, this is just our numbers, in case you like numbers and not graphs.
So we went back.
So
in 2020, Hamel published a report, and this was a long multi-year working group project to solve the paradox of short period building seismic performance. Because, oh wait, is the previous slide hidden? There was another one in here.
Oh.
Takeaways?
Yeah, no, there's two if you escape out of it.
Yeah, it didn't work here. This where we're.
Down.
Oh.
Okay.
Did you try my Dropbox?
Yeah. Well,
Not right.
no, I wonder if I opened an older version, would it?
There's a slide.
There's some
It's
extra
not-
slides at the bottom.
but, yeah, it's not
See
that.
that?
So
Okay,
this
sorry
is-
about that.
But basically, in this document, the reason that this project began is that they were finding that there was a really high probability of collapse in short period structures. So residential wood frame and masonry were kind of the big focus. There's a third one. Steel
yeah,
platform.
Steel,
Yeah.
steel brace frames.
So
I see, yeah.
basically, they undertook this project to figure out why the models, which, you know, were kind of using the same protocol as other methods that did align with actually observed post-earthquake performance, why short period buildings have this big spike. And so the figure that's missing here is this like curve showing the probability of collapse versus period. And it's actually just figure 1-1. So if you find this document, it's like they're explaining kind of this was our concern. And the volume 3 of this is about wood frame buildings. So I used a lot of that in developing the models, but they use software, different software that's also now obsolete. And we went back.
So the moral of the story is we're not the first people to discover
We're not?
this, right? Like, this is a known phenomenon that seismic modeling of structures for short period buildings is out of whack. Nobody really knows why. So that's what and it's also worth noting that the 2020 publication date aligns with the beginning of the project, right? Like this wasn't really out until basically we already started.
So in the real world, they perform better than they model for short structures.
Yes, that's what the paradox. That's the paradox,
Yeah.
right? They're saying that you look at the earthquakes and we don't have buildings, you know, wood frame short period buildings falling down. So, but the models say they should be. So what's the problem? So.
And so what we found is that basically they are including architectural walls as seismic system or as lateral force resisting systems. They're modeling the sheetrock. And so you're getting a much stiffer structure. And so with these corrected masses, and I was saying this morning, basically what we're doing is modeling like you just build just the structural parts of the house, and then you pile up the rest of your building material and you bolt it down to the floor, and then a big earthquake happens. And that's kind of the worst case scenario, is that you have at a bare minimum lateral stiffness and your entire seismic mass.
So is SF2, when you say anything at 6, have you provided the code minimum allowable shear wall? Okay, so could that be like a little extra, like in your actual SF2 has?
Yeah.
On more than literally the code.
Yeah.
Yeah.
And then that's what they did in this,
Oh, they
this
all-
paper is that they added in, they used the term like architecturally, you know, common or something like that. And they were like, you know, if you actually had a house this size, you would have all this extra stuff. They included the sheetrock on the back side of the shear walls. They included the sheetrock walls in the middle of the building. They gave them some stiffness, and then they also included larger drifts and residual strengths, because things probably wouldn't actually, like in the lab, it just goes to nothing because we're jamming on it with an actuator, right? Whereas in real life, it would probably not go to nothing. And so they did all that, and then they came up with like probabilities of collapses in models that were more in the 10% range. That didn't really help us. I was hoping to read this document and be like, oh, what do we do? Like, what is the like, you know, the thing that you're supposed to do with your model to make it work? And they didn't say that. They just sort of said, we solved the paradox because we added sheetrock. So, but I think that our results are still interesting. It's actually interesting to look at our initial results, I think, because reducing the mass is another sort of the same thing, if you will, as adding more wall, right? We're just adding stiffness in a different way. And so seeing the probably, and the secondary results or the corrected results are not actually as fun to look at because everything's falling down. So you don't see these stark differences between the, 6-inch nails and 12-inch nails or the staples and stuff. And so the initial results are actually kind of more useful. So these were some of our takeaways. It used to say design codes work. Now it says design codes work probably, right? Because the models say they don't, but they, experience says that they do. And then, the closely spaced fasteners increase ductility and strength. Probably all aware of that if you saw the testing. Then, as I've already mentioned, the nails are more ductile than staples. T111 should definitely be double nailed. I kind of mentioned that it wasn't a huge difference, but it definitely was a difference. It was a 30 or 40% increase in the strength and ductility. You had both rows of nails.
For like very little additional work.
Right. And then, dynamic modeling. Building to the car. That's our takeaway. Do you have more slides? I think we have some thank yous maybe. But yeah, and since this is a FEMA project, their FEMA, of course, is very interested in mitigation, right? So they wanted us to know, they actually wanted us to do a whole lot more with the project. Outreach and, talking to people about various, this sort of thing, well, talking to framers and citizens, who may be voting about building safety areas or not, those kinds of things, which we didn't get to do as much as we wanted to initially, partly because we were struggling so much with the amount of work it was to do these criminal. And so, mitigation strategies for people who are not structural engineers, or add more nails. And then when you're done with that, add more nails. So,
Everything's bolted.
and make sure your hold downs are actually heading up on them. Right? We didn't say this in specific, I guess we did, the first one, enforce building codes, right? And the idea here is like, you need to have inspections in the river. Because otherwise, ideally our initial, if you just look at the numbers from our initial stuff, which was really good, you could say things like, we drew conclusions like, you're 5 times more likely to have a collapse if you double your nail spacing, right? Huge number, right? That's $9 worth of nails and cut your risk of death.
Do you know the history of the demonization of those 16 gauge staples? I built a house in 1979 and I was
Speak up.
16 gauge staples, and then a couple of years later they were banning them and they wanted everybody to use 14. Anybody remember
Do you
that?
remember?
It can get really still in there.
They're still in there.
Yeah.
I think so. One of the framers told me that he could kick the OSB off the wall with the 16, but not the 14.
Yeah.
And
So, we also didn't look at.
like, well, that's
That
not
would be-
what we're doing. Yeah.
Yeah.
So they're supposed to be in shear, right? We don't really care if you can kick it off.
Yeah.
So.
But the wind.
I was just curious.
I think it has more to do with the equipment and staples, just the cost of the staples themselves.
Yeah.
If you ever hold those 14 gauge staples in your hand, they're
They're-
huge,
they're
they're heavy, probably cost all.
The beauty of those 16 gauge staples is you could put them in at 2-inch on center and not damage your studs at all.
Yep.
I used 100,000 of them when I built my little house.
Yeah. Yeah.
And it was money well spent when we had this earthquake and, a few years ago, this one you're talking about, I didn't have any damage.
14 gauge is not even in IRCA.
Okay,
So it's really,
I
interesting.
think it's in the previous version.
I also did not use any OSB. I stuck with half-inch CDF.
just to have a bunch of thank
Olive
yous. Yeah.
wood sheet to apply with it. Okay.
Simpson was very nice. They gave us all of the hold downs for free,
Nice.
which is good because they're cheap. Corbin, our machinist Corbin, he ended up building a lot of them for helping students build a lot of the walls. Because there wasn't really much else going on because of this building. So he was pretty upset about that, not liking walls.
Well, he liked it because he kind of like shooting guns of any kind. He didn't like but I would mark out where the nails.
It's a
go.
lot of being on knees and.
Yeah. But
Okay.
nice record.
I would suggest you get with the Alaska Home Builders who are trying to get the state residential code adopted, and they might be able to fly you down to Juneau and present this to the legislature and their staff and get it off the time.
Maybe we'll change it.
Yeah, you might have to dumb it down a little bit.
Different audience.
Different audience, but
Yeah, and
but the conclusions are the important part.
that's a good.
But it is a big question now, like. There's simply, yeah,
We tried to, and we actually tried pretty hard to interview for them. We did talk down Grace and Ellie, but a lot of them didn't return a call. So
And there's a dispute among the home builders. The Matsu home builders don't want it, but the Alaska one and the Kenai do, Anchorage do.
Yeah.
And partly it's because the Anchorage home builders also build in the valley, and they build the same there they do here.
Right.
And the Matsu home builders go across the street and can sell it for 20,000-30,000 cheaper because they're not following the IRC.
Right.
Now, all the inspections are going to be the same as they do anywhere now. It's hired by the contractor. AHFC requires them. But if they screw up, there's a way to sue the contractor. Right now, if you're outside Anchorage or some of the other communities that have IRC, if they try to sue the contractor, they say, well, I built it the way I always built it. There's no standard that I have to meet. And the case goes away.
Any questions online at all? Put it in the chat.
so the kind of going back to these models, and figuring out the mass question is that we ran the SIPs, which are stronger and about as ductile, and they were doing very poorly because I like recreated the model with the appropriate masses. And it was like, well, this doesn't seem good. You know, the SIPs should be better than the stud walls based on the testing. And they, the same design process should be meeting the same standards. So now they match, but in a way.
we were getting like probabilities of collapses of like 80%. We were like,
It's a good.
I mean, yeah, they're a little stiffer, but what the hell's going on? Now they're the same. Look terrible.
All right.
When you publish the results for the SIPs, are you republishing this with the appropriate methods? Because I would love to compare the two.
Yeah.
To offer some objective evidence to folk out there that want to compare the two. But I can't. I only have the old methods and the corrected methods.
Yeah, so we need to, we haven't done that yet.
Okay, it'd be helpful.
Yeah.
When we get the new SIP publication that we will be using.
Look really bad.
But I don't want to compare it to the old
Yeah.
mass, because that's.
Yeah, so that's a good point. Yeah, unfortunately, the report that we submitted to FEMA as our final report had all the old stuff, so it looks really good.
And I wouldn't say it's wrong, personally. I would say it's a very open concept.
It's a pavilion with 8 feet of.
Yes. No, it's just low mass, right? And mass is variable and you still has value. You guess at a mass, but the changed mass makes it hard to compare.
Well, and we could go the other direction too, right?
And you could go the other direction.
With low mass, sensitivity.
An open concept.
And it's
A lot of them out there these days.
you run
Houses
it,
don't.
like the spectra that I just saw a little bit in the weeds, but basically we take the spectra, the frequency content of each of those 22 ground motions, and then we take the 2 orthogonal directions, take the geomean, and then that's what we're scaling.
Okay.
And so that spectra is all based on the single degree of freedom model, which is you're just matching, period. You're not, your mass and stiffness would be wildly different, but if you have the same period, then your single degree of freedom will have the same response. And these are not quite single degree of freedom models, but having that rich diaphragm means that they kind of behave, and the masses are all applied at that floor level. And so I think that the initial results are probably closer to, I was told never to say accurate when talking about modeling, but sort of close to reality, but
I appreciate
I don't think that we can
both useful.
arbitrarily,
Most useful thing
Yeah.
compare.
Right. but definitely just like having or quartering the masses is not like a defendable.
Probably not.
This is my,
We
yeah,
didn't like it, so we just cut the mass in half.
yeah.
But it does point out the difference between, for example, 6-inch nails and 12-inch, right? Which is a really big difference. And, but the projectile framer, you know, they might be like, what's the big deal? You know, it stays on. It still looks pretty solid with, you know, 1/3 less nail, whatever. Just have to kind of be like, well, you're roughly doubling the probability of collapse, probably. For a long time.
Thank you.
Thank you. guys.
Thank you.
You guys already have one of these? I don't got them off yet. Drop them off.
I'd love to see that.
How you doing?
How are you?
Good. Busy.
Start getting,
How you been? Yeah, pretty.